I thank you so much for joining, and I thank you so much for this opportunity to introduce about our effort to use AI-based model framework to see the relationship between the climate change and dengue prevalence. So again, my name is Do-hyun Kim, and I'm working as a lead data scientist at UNICEF. And I'm joined by my colleague, Hanuk Balabi from UNICEF as well. So let me hand over to Hanuk so that he can briefly introduce about the context of our work.
Thank you, Do, Marian, and distinguished participants. Honored to participate in such an interesting conference. Also to start, and Marian, to say that the interesting thing is that it's not by coincidence that we are today talking about health and climate, as we're realizing that they are getting more and more close to each other, and therefore we have to start changing a bit of the way we are looking at both climate as well as the public health sector. And starting with the dengue, we all familiar with, probably today we hear about the dengue. The fever is one of the most common and rapidly spread arboviral disease in the world. Is a major public health and socioeconomic consequences. We started and investigated a bit further in the Amazon basin as UNICEF, working with government and different entities on that subject. And just to get a bit of a background, it is important to understand that that comes also from the climate perspective. According to the IPCC working group for the Latin America and the Caribbean, as part of the assessment report, the sixth assessment report, the climate change affect the epidemiology of climate-sensitive infectious diseases in the region and as in other regions. Example includes the effects of the rising temperatures on increasing the feasibility of transition of vector-borne diseases, including the endemic and emerging arboviral diseases such as the dengue, chikungunya, and Zika. For example, the production of potential for dengue transmission increased between 17% to 80% for period between 1950-54 and 2016 to 21 respectively. Depending of course on the sub-region as a result of changes in the temperatures and the precipitations and other factors that we will learn today. More specifically, and we delve a bit more into the Amazonian Peru, a region that's called Ucayali. What we learn is that really the main vector-borne disease are those transmitted by the Aedes aegypti that you probably all familiar with, the dengue, Zika, yellow fever, chikungunya. The vector Aedes aegypti is sensitive to changes in temperature and precipitation as we learning with the time, and therefore we could also start to anticipate the different and the changing reaction and behavior. For that extent, the Ministry of Health in Peru in 2016 conducted a technical assessment how climate change is in fact affecting the public health situation in Ucayali region, and managed to identify risk and recommendations on the anticipating health risk under the climate change and on all the variabilities related to. And that is where we are coming next, please, Edo. And that is where we are coming a bit, we as UNICEF, in supporting government, in particularly the health sector. And what is the hypothesis? That where we are all starting from, that the dengue is a climate-sensitive disease. Temperature and rainfall variations influence the magnitude and the seasonality of a dengue transition. However, what we're actually realizing that there is a huge challenge on the countrywide level, since dengue incidence varies across administrative areas, considering also climatological and socioeconomic attributes. In different areas, we saw different behavior, which connecting all those different variations. So actually, what really the task is nothing really strange and new, but it is what is it really came out as a strong task, as a strong challenge, is that how can we anticipate such trends that can help governments to implement an effective control measures and obviously mitigating the effects of the disease. And just to summarize this, it is really what we realize is the importance that public health policymakers, vaccine developers, and vector control specialists be provided with a robust estimates of the current and future and local distribution of the dengue. And that is where really it connects us the dots, and I bring Do from the scientific perspective. Over to you, Do. Thank you.
So with this given context, we have explored different options to accurately model this dengue fever prevalence. And we noticed that recent AI technology can dramatically increase the model performance and accuracy, especially where there are some missing data and noises in the data set. And then when there is a complex and non-parametric patterns in the data. And then we also identify that recent AI technology is extremely good at in long-term forecasting, and also much easier to do the feature extraction, which is done within the data set itself. However, we also noticed that in some cases, the traditional machine learning or statistical based model could work better. So we decided to, rather than depend on one single approach, but develop ensemble or harmonize the model between the different type of the models, incorporating the recent AI technology and the traditional type of the model. So this has been developed as this ensemble frame AI model framework, and we, as Hanok briefly mentioned, we started with the context and the background in Peru. But when we started this project, we soon realized that the Peru data set for the dengue case was not really complete. So there are a lot of missing data in especially some of state and department. So we moved on to finish this model development in Brazil. And the model development has been successful in Brazil, and then again fine-tuned with the available data set in Peru and successfully applied in Peru context as well. So this work has been identified as the one of the global top 100 AI project by IRCAI under UNESCO, and also identified as a best of UNICEF research for 2022. So to develop this ensemble AI and machine learning framework, we have tested different climate and environmental variables. So majority of those data from Earth observation data, and also some of the geographical climatal data also explored. So this is not the entire list, but we tested using the vegetation or forest cover data and the NDVI and the height of the elevation from SLTM data, and other climate data observed by this satellite sensors from European Space Agency. So this shows briefly the type of the data that we have used in Brazil, including dengue incidence data for different states, and briefly showing the relationship with the air temperature and humidity. So you can see in many cases it has a very close relationship in terms of the pattern. This is the data that we collected from Peru, including dengue incidence rate. But also you can see that in some department and state, you see many dengue cases omitting from them, given that some loose relationship with the maximum air temperature and humidity. So that's actually one of the reasons that we drove our decision to first implement this algorithm framework in Brazil. So this briefly explains about the type of the AI framework that we have been developing. So again, this has been done in Brazil. First, we pre-processed those time series data that we've been collecting from satellite, remote sense data, or other socioeconomic or geospatial climatal variables. To reduce the data dimension and make it much easier to deal with the machine learning framework that we're developing, we applied the spatial correlation convolutional neural network. After we reduced the dimension of the data set, we applied different type of the machine learning algorithm, including CatBoost, SVM, and LSTM, long and short-term memory. So based on this machine learning framework, we could combine different observations using the random forest at the last stage, so that we can finally get the dengue incident rate for the individual department. So this has been successfully implemented again in Brazil. And then, as you can see, we collected those similar data in Peru. And then we could fine-tune this ensemble AI machine learning framework, and then again applied in Peru. And then the results were much improved compared to our first approach developed in Peru. So this is actually kind of opportunity that we realize in between this development of AI algorithm, and that our model first developed in Brazil with the very good dengue cases data can be scaled up into different places, and even to develop the regional or global scale model. So here I present some result for Brazil from our model. So you can see that the green line is the baseline prediction from some previously developed model based on Bayesian statistics. And the orange color line shows the actual observed cases in Brazil. And the red line shows the ensemble AI framework-based prediction of our own. So you can see that compared to the baseline prediction from different model previously developed for Brazil, our prediction improves much. Compared to the previous one, much closer to the actual observed cases in different states in Brazil. So this is the another example of our result showing the the prediction across to the actual observed cases in different states in Brazil. So again, we fine-tuned this model and applied in Peru. So you see the results from Peru. Compared to the result from Brazil, our prediction is less, fit to the hikes in terms of the dengue prevalence in some places. But still, you can see that our model outperforms the previous existing model. So we can see that there is a lot of advance and progress in terms of the model prediction, but still we may need more the cases data, more accurate data to make it more fit to the actual observation. So that's a brief introduction about the how we build this model and how the results was look like in different places. So Hanuk can again talk a little bit about our future directions based on our success in model development. Hanuk, please.
Thank you, Do, and really as a natural continuation of this work and results and conversations with health sector, with different entities, other UN agencies, government, obviously, science, academic. We thought that there is a space to continue and excel this work. In a nutshell, we put in four work streams that we see this moving ahead. And first, and as a overall umbrella, it's the expansion on geographies and diseases. As we could see, as mentioned my colleague Do, we would definitely want to look at this beyond the Latin America region and see how that could work in other places in the world. So the whole idea is that really using how can we operationalize it? How can we take it down to earth to make it as a management risk tool, as creating a platform, an open source platform that could be used by the health sectors and the different relevant stakeholders to better prepare and respond to future changes in the dengue, in current and future in the dengue risk and incidents. What we also would like to continue is to advance all the scientific knowledge on environmental epidemiology, geographical and climatological factors that are responsible for triggering different types of disease transmissions. And I will end up with our really vision on the way forward and saying Excel creation. A fundamental component is the linking the different disciplines, different sectors, different institutions, and really further promoting the collaborative work among complementary expertise from an intergovernmental organization, public health, and academic institutions to advance knowledge and address social challenges. And all this becoming and end up in enabling the condition for safer and healthier environment for children and their communities. And we will stop here and pass it over back to you, Marianne. Thank you very much, and looking forward for a conversation after the following presentation. Thank you.